The Solaris Synchrotron is a device which creates extraordinary light. We familiarize light with the sun, electric bulb or a candle. In science, however, light is electromagnetic radiation. The light that's visible to a human eye is a tiny bit of the radiation that is ever present in nature and accompanies humanity in all their endeavors. The primary source of the visible light is the sun, which also emits the ultraviolet radiation, causing the suntan effect. The infrared radiation is perceived by animals and people alike as heat. Another infrared spectrum allows us to use remote controls which communicate with our TVs. Traditional radios transfer information via radio waves. Microwaves heat our food. Mobile phones use another spectrum of microwaves to communicate with the relay stations. Medical X-ray photos are a result of a body exposed to a high-energy electromagnetic radiation. The Solaris Synchrotron creates electromagnetic radiation from infrared to X-rays. That is why scientists can use a broad spectrum of waves, which creates vast research opportunities to learn more about the matter. End stations located within Solaris use mainly X-rays alongside ultraviolet and infrared radiation. Synchrotron research uses light in various ways. Scientists can expose different objects to it, hence producing their images. They can see how a sample fluoresces and obtain information on the concentration and content of elements within it. Light going through a material can create a diffraction pattern, and mathematical methods allow to recreate the molecular structure. Put differently, you can collect data on how many atoms create a material and what is their structural layout. Synchrotrons also use the photoelectric effect. Light can knock electrons out of the material. Special detectors capture these. They allow for researching the electron's energy, momentum, and spin. Such knowledge allows determining both physical and chemical properties of the entire sample. Synchrotrons allow researching different materials and track occurring changes caused by electromagnetic radiation. Each spectrum provides a different set of data. Moreover, scientists extract a different kind of information from the image of a sample once it fluoresces. Another set of data is gathered through measuring absorption, applying diffraction patterns, and the photoelectric effect. Synchrotrons are sources of universal knowledge when it comes to the matter. The Solaris Synchrotron is the largest research infrastructure in the history of Poland and one of the mere dozens of synchrotron light sources which function in Europe. 3 electrodes are needed to create the synchrotron radiation, which can be used in research. The electron gun produces them, and then electrons are accelerated in a linear accelerator to an incredible speed which is close to the speed of light in vacuum. In 1 second, they can travel nearly 300,000 kilometers, a distance between the Sun and the Moon. Speeding electrons are injected from the linear accelerator into the synchrotron. Thanks to the power of 12 electromagnet blocks, their path is curved, hence they move on a closed orbit while emitting synchrotron radiation. To curve the paths of electrons, Solaris uses 12 integrated electromagnet blocks. produced according to an innovative Swedish design from Max 4 laboratory. The insertion devices such as undulators and wigglers can be placed in the straight sections connecting these blocks. They create additional synchrotron radiation. The synchrotron is a small sun on Earth, a sun which shines with extremely bright light. Not only infrared, visible and ultraviolet, but above all X-rays which penetrate through things. Beam lines are connected to the place where the synchrotron radiation is produced, that is the electromagnets and insertion devices. Components of these lines select a specific range of radiation, focusing a stream of photons on a sample placed in a chamber of analytics station. The Solaris synchrotron can deliver its radiation simultaneously to a dozen of beamlines. There's a group of specialists working on the production and providing scientists with the synchrotron light. Accelerator physicists optimize the stream of electrons. Scientists, along with engineers, look after the beamlines. Engineers of different specialties ensure the stable power supply, electrons acceleration, free movement of electrons in ultra-high vacuum, cooling different components of the synchrotron, and finally, gathering, processing, and sending thousands of signals which direct the synchrotron. The synchrotron operations are supervised by the Radiation Protection Officer. The synchrotron is utterly safe to the environment, even though while working it creates harmful electromagnetic radiation. Safety is ensured by special radiological barriers following strict access protocols to all dangerous areas and constant monitoring of the radiation levels. There'll be more than a dozen of unique beamlines in the Solaris synchrotron. These will allow groundbreaking discoveries in many disciplines of science. The research will be conducted simultaneously at many stations, 24 hours a day, 7 days a week. Thanks to this factor of research, Polish science enters a path of development which has been followed a long time by all high-developed countries. The Solaris synchrotron is an amazing device which allows for groundbreaking research of the surface, the inside, and the structure of materials. Synchrotron creates unprecedented capabilities for the scholars because it is the sole source of electromagnetic radiation, the light of such unique properties. Synchrotron light is amazing because it includes a broad spectrum of electromagnetic waves. To carry out a measurement, devices located on the beamlines pick a certain length out of that wide spectrum. Smooth changes to the lengths are possible as well, just as in the radio when we search for a particular channel. Also, the synchrotron light is exceptionally bright, often 1 million times brighter from light created by other available sources. Thanks to these characteristics, many measurements can be conducted only in the synchrotron research centers. Such measurements are quicker and more effective, while results are qualitatively better from the traditional methods. The SOLARIS Synchrotron N stations test numerous types of materials, mainly solid as well as ultra-thin layers, which can be a single atom thick. Amongst the tested materials, there are different kinds of electric conductors, metals, alloys, semiconductors and insulators, as well as mineral samples and so-called composites. In majority of cases, synchrotron measurements are conducted in the ultra-high vacuum. Hence, it is necessary to prepare samples properly. It is crucial, especially while studying the surface of objects. To reveal it, the sample needs to be purified in vacuum chamber through the process of breaking, bombarding it with ions of noble gas or heating it in a few hundreds of Celsius degrees. The measurement subject can also be created by placing its thin layer over a selected base. Sample measurements take place in analysis chambers. These hold a special place for a sample, which is targeted by synchrotron light while equipped with suitable detectors to analyze signals. These can be, for instance, number and energy of electrons emitted from the sample or the number of photons emitted after radiation has been absorbed. This way, the SOLARIS Synchrotron N stations can test the chemical composition of a sample, its atomic and energetic structure, as well as electrical and magnetic characteristics. Both chemical and electron structure of samples determines their essential characteristics. Studying them, we find how does it conduct electricity and how it reacts with light and magnetic field. This knowledge is inevitable in designing more efficient electronic devices, for instance, processors which are faster and use less energy. Materials used in the solar panel production have been tested for years to increase their capability of turning solar power into electricity. Finding more about magnetic characteristics of materials can help to produce faster ways of storing even more data. Diffraction studies of protein structure and other biological molecules lead to increased knowledge of life processes and help to form new drugs. Many of the synchrotron measurements are fundamental, and their purpose is to obtain new knowledge on the material structure and their inner processes. This knowledge lays the foundation to the discoveries and finds a practical application. Fundamental research stands behind the LED lights and modern TV and mobile screens. Many industries use the synchrotron research, for instance, aviation, automotive, chemical, pharmaceutical, electromagnetic, energy, and the food industry. The SOLARIS Synchrotron is the accelerator of the innovative economy.